What I still owe you is a definition for mutual exclusivity, or mutex, between actions. And again, I will start by illustrating this with an example. We are looking at the same planning graph as before here, but now our first layer we're looking at is the proposition layer P1. That was on the right-hand side in the previous graph. So we have P1, A2, and P2 in this graph here. And I'm sure you will remember from the previous example that in proposition layer P1, the propositions R1 and R2 were incompatible. So they were mutex. Now, we know that our proposition R1 is a precondition for the action LAR1 in our action layer A2. And the proposition R2 is a precondition for MR21 in the same action layer. And it should be clear to you that if these two propositions that are preconditions for these two actions are mutually exclusive, so they cannot be true in this proposition layer together, then the two actions cannot occur in the following action layer. So these two actions must be mutually exclusive here. So what we've seen now is that mutual exclusivity between actions can lead to mutual exclusivity between propositions in the following proposition layer. And the other way around, mutual exclusivity between propositions can lead to mutual exclusivity in the following action layer. And now we can formally define what it means for two actions in the same action layer to be mutually exclusive. And this definition is quite simple. We can say that two actions A1 and A2 that are in the same action layer AJ are mutex if one of the following two conditions holds. Firstly, if A1 and A2 are dependent, so if the dependency we've defined earlier holds between these two actions, then they're also mutex. Or a precondition of A1 is mutex with a precondition of A2. If there are preconditions that are mutually exclusive, then the two actions are also mutually exclusive. And these are the only two reasons why two actions in the same action layer may be mutually exclusive. Note that the first of these two conditions is problem independent, so dependency does not need to be recomputed for each action layer AJ. It's always the same whether two actions are dependent or not. Whereas the second condition does depend on the action layer in which the two actions are, because we're referring to preconditions which are propositions in the preceding proposition layer. And now again a bit of notation. I want to introduce the set mu aj, which we've already used in the previous algorithm, which is the set of all pairs a1, a2 in an action layer aj that are mutex. So these are all the mutex pairs of actions in a given action layer, namely the action layer aj. And I can now tell you that in the example we've just looked at, in the action layer a2, there were actually 24 mutex pairs of actions. That may help you to understand why I'm not drawing these mutex links into the graph every time I draw the graph. And a final remark about the mutex relation, and this applies to propositions as well as actions. This relation is symmetric, so if A1 is mutex to A2, then A2 must also be mutex to A1, and again the same goes for propositions. And again, for those of you who prefer an algorithm to a definition, here comes an algorithm in pseudocode defining the function mutex for a given pair of actions and the set of mutex proposition pairs in the preceding proposition layer. And in this algorithm, we simply test what we've just defined, namely, the first thing we do is we test whether the two actions are not independent. So if these two actions are dependent, then they're also mutex, which means we return true. Otherwise, we have to look for a pair of preconditions of A1 and A2 respectively, and these are the preconditions P1 and P2, and see whether these preconditions are mutually exclusive. So if we find such a pair of preconditions for these two actions that are mutually exclusive, then we know these two actions are also mutually exclusive. If we cannot find such a pair, and the two actions are independent, then we return false, meaning A1 and A2 are not mutually exclusive. As for the time complexity of this algorithm, you can see it consists of two parts. So we have the time complexity of the first part plus the complexity of the second part, and this is simply O of b squared, where b is the maximum number of preconditions and effects we have per action. Now that we understand what mutex relations are and how to compute them, I want to see how mutex relations propagate through the planning graph, and that is quite important. So we have two propositions here that tell us how mutex relations propagate through the planning graph. And the first one says that if we have a pair PQ that is in our proposition layer Pj minus 1, and they are not mutually exclusive in that layer, then this same pair of propositions will also be not mutually exclusive in the next proposition layer. This means once a pair of propositions that has appeared as mutex in the planning graph, once this pair has become non-mutex, it can never become mutex again in a later layer. So the mutex relations are in some sense decreasing the further down the planning graph we go. And to see that this is true is actually quite simple. So we assume that P and Q are in our proposition layer Pj minus 1. And of course that means we have the no-op operations for these two propositions in the following action layer. And we have assumed that the propositions P and Q are not mutex in that proposition layer. So that means the two no-op operations are also not mutex in their action layer. And that, of course, means we have a non-mutex pair of actions that produce P and Q in the next proposition layer, and that means they can't be mutually exclusive. And we have a similar proposition from the mutex relation between actions, namely that if two actions are in one action layer and they are not mutex in that action layer, then they're also not mutex in the following action layer. And again, the reason for this is quite simple. So if we are given that A1 and A2 are not mutex in this action layer Aj minus 1, then by definition that means A1 and A2 must be independent, and their preconditions cannot be mutex in Pj minus 1. Now, I've already told you in the previous proposition that because mutual exclusivity between the preconditions carries forward, the preconditions for the actions in the next layer must also not be mutex, and of course action independence is constant. So what this means is both of these properties remain true for the next proposition layer, and hence our two actions remain independent and therefore mutex. So this is a very important property of the mutex relation, that it's decreasing with increasing layer. That's true for propositions and for actions. And we will get back to that later. Now, before we move on with the graph plan system, there is one further refinement to the planning graph that I want to introduce to you. And this is actually quite simple now that you understand the mutex relations between propositions. So, suppose we have two propositions P and Q that are mutex and that are preconditions for the same action. In this example here, we have the action UAR2, and it has two preconditions, R2 and AR, and they are mutually exclusive. That, of course, means that we can never execute that action UAR2 in that action layer. And what we do in this case is simply remove the node that represents that action and all its edges from our planning graph. We remove UAR2 from A2. It's as simple as that.